Section 12.3 is going to continue this idea of surface area, but involving cones. We've seen it already in 12.3 with surface area pyramids. Now, why would cones be in the same section?
Well, I know that both cones and pyramids have just a single base.
Okay.
And then they kind of meet all this lateral stuff up to a point, the vertex point.
So they have some similar features. Now, what makes cones different?
Well, cones have a circle base, and there's really not any faces per se on the lateral stuff that goes up to that point because it's just one big curved surface.
So would it be fair to say that a cone would not be considered polyhedron?
It is not a polyhedron.
So that's one of the major differences. But I like how you started with kind of the fact that why are these going together? Is because cones and pyramids have that one base. So it's a solid. This one base is a circle. It's going to have a vertex where basically all the other stuff kind of meets in a sense. Notice that vertex, it says it's not in the same plane as the base. If it was in the same plane as the base, it would not be a three-dimensional solid.
It would just be a circle.
So here's kind of a visual, just to give you ideas of what a cone would look like. Right, here's your circular base, right? Your vertex would be somewhere up here, okay? It could be down below, just wherever, right? This is kind of give you a visual of that. Now, some vocabulary goes along with it. The next basically few terms, we've seen these things before.
Yeah.
Okay. So let's start with altitude or height. All right. This is, again, the perpendicular distance between the vertex and its base. So if I draw a segment that's perpendicular from the vertex to the circular base, like I have here, this would be considered the height. Okay.
Okay.
Now, this cone is kind of unique because it's a right cone. And if you read the definition, it'll explain why. A right cone is a cone where the height meets the base at its center. So notice I drew in, this is that perpendicular distance, this is your height. Notice it goes right dab to the center of the circular base.
Right.
Most cones that we deal with are right. Okay, if you think about any cone out there, most of them, like a party hat, right? Ice cream cone, depending on the type of ice cream cone, is a cone in a sense, okay? A right cone. Now, slant height is another word we've seen. We've seen it with pyramids, okay? Again, that connection. We've seen it very briefly with prisms, but didn't do anything with it, really.
Right.
Pyramids and cones is where we see it mostly. And the reason why is because it's a special distance. It's a distance between the vertex, so that point right here, vertex, and a point on the base edge. Now, what I mean by base edge, what do I mean by that?
Well, usually when we talk about base edges of a polygon, we're talking about the sides of a polygon.
Which are segments.
But here, I don't really have a single segment, but so it's somewhere on the circumference of that circle.
Basically, a point on that circle. So if I go from here to here and draw in a segment, that, or kind of connecting those, that would be considered the slant height, right? A lot of times when you see the slant height, you'll see it because this is, again, three-dimensional on a two-dimensional surface. You'll see it go from here to like here. So this would be considered the slant height.
Right.
Okay? Now, a lateral surface is basically what, to me, when I see lateral surface, I think of anything but the base or bases. In this case, just one. So it's the surface of a cone that consists of all the segments that connect the vertex with the points on the base edge. So basically, if you just draw in a bunch of slant heights, okay, just keep drawing them, you're making up that lateral surface. If you think about a party hat, the party hat itself, the material, is the lateral surface. What's open up so you could fit it on your head is your base, okay?
Right.
Because it's the circle, all right?
Okay.
So just kind of give you a visual of that. Now, to show you some bigger pictures of some cones, to show you some differences too, the one on the left is considered a right cone. Why?
Because its vertex is lined up with the center of the circle. So that's where your height actually falls.
Exactly.
Perpendicular
And
distance.
this would not be considered a right cone because if I draw in the perpendicular distance, which again goes from the vertex to the base, and make it perpendicular, that doesn't go to the center. So that's why that's not considered a right cone. We spend more time with this. This would be more of an oblique cone.
Okay.
All right. Again, the slant height, a lot of times, like when you draw it, there's your slant height, goes from the vertex to the base point on the circle. And then we call this the
radius.
Radius. And
the
notice what's kind of unique is that you see a
right triangle.
So might come into play. We'll see. All right, let's talk about surface area. I'm going to have Ms. Hoggery take over.
All right. So we have a formula, of course, to find the surface area of a right cone. And just to talk about what pieces make it up, we know surface area, we have one base that we need, so we don't need two bases because it's not a prism. We have one base, and then we have all this lateral area, okay? The actual formula, we know that when I talk about the area of a base of a circle, we're talking about pi r squared. So this right here is the area of the base.
Which makes sense because it's the area of a circle.
Exactly.
So guys, here's another formula we're going to add to our list. It again, something else we got to remember, but if you really break it up, area of the base is a circle, pi r squared. That's easy.
So hopefully one we know.
We know that.
Now, the lateral area, we actually use pi RL. Now, let's talk for a minute because I want to try to make some connections for us. When we talked about a pyramid,
we were able to prove that formula, right?
We were able to prove that formula pretty easily, actually. What was the formula for surface area?
It was surface area equals area of the base, and it just depended on what type of base it was.
Right.
Plus 1/2 the perimeter times the slant height.
Now, in this case, we can't really talk about the perimeter so much of our base. We usually, in a circle, talk about what?
Circumference.
Circumference. So instead of saying half of the perimeter, we could say half of the
circumference.
Half of the circumference times the slant height. Well, the circumference of a circle is what?
2 pi r.
2 pi r.
If I do half of 2 pi r,
that would just take away the 2's, so it's just pi r.
That makes sense.
So this really is still the area of the base. I could use this as another formula if you want to. Area of the base is equal to half the circumference times the slant height.
Put plus instead of equals on the second equals.
Oh, thank you. Yeah, so this is really another way you can think about it. It's the same basic formula. It's just the idea of, sometimes I have students that like the pi r squared plus pi rl. They kind of remember that. And especially if you struggle with remembering the area of a circle as opposed to its circumference.
Exactly.
So,
but I like that connection, Ms. Hoggery, because this, to me, then it's less formulas I have to remember. If I can remember, because I noticed with prisms and cylinders, they had essentially the same formula. With pyramids, with pyramids and cones, they essentially have the same formula for surface area.
They do.
Makes it easy.
All right, so I've got a picture down here just to kind of talk about, this would be obviously my
radius.
So when I say pi r squared, we're talking about finding that area of the base. That's where that's coming from. And then again, that pi r is that half of the circumference times the slant height. Where would the slant height be on this cone again?
It's more the point. It goes from the point, the vertex, to a point on the base, which would basically be, if I kind of do more of that diagonal there, that's your slant height. So I notice here I don't need to know the height to find
we do not
the
need
surface
the height.
area. Whereas, and this is where, again, making connection. When I needed the height was when it was a cylinder or a prism. And I'm noticing with that, you had two bases. With a cone and a pyramid, you don't need the height because of the fact that it comes to a vertex, a point. There's only one base. So that slant height's important.
Right. Now, we've drawn over here a net. The nets of cones are really weird because you know you have your one circle for your base, but if you've ever unfolded a party hat, you'll see that it doesn't make a full circle. All right? Because if it made a full circle, then obviously you wouldn't be able to join two parts together to form that three-dimensional lateral area. So it looks like a Pac-Man to me. That's what I always think about it. And it's like a sector of a circle.
Yeah.
So what you're really doing is you're finding the area of the base and the area of the sector of the circle.
Okay.
Okay?
All right, let's put this to use. It says, find the surface area of a right cone. So again, we've kind of done some of these now so far. This is basically the fourth surface area type problem we've seen. And if you see the word surface area and you see right cone, I'm going to immediately write down the formula.
Yes.
So I'm going to say surface area equals.
Let's go with pi r squared plus pi rl, just to be able to get there.
And guys, this is something you can remember. If you don't want to try to remember all these different separate formulas, maybe make connections between the ones that have similar features, okay?
Sounds good.
So in the surface area formula, I'm noticing I need to know the radius, and I need to know the slant height. So I need to know really two things. That's it.
That's kind of nice.
Right, so let's look at the cone that they're giving you. And they're telling you it's a right cone, so that's why we can use this formula. What information are they giving you?
Well, they do give us the radius, which is great. They give us that's 5.
Okay.
However, they don't give us the slant height. They give us the actual height.
So I'm going to put H for that. Now, is that the same thing as the slant height?
It's not the same.
No, and if you kind of think about it, this is the height, this is your slant height. The height is actually smaller than the slant height. So we have to find that slant height first.
But we do notice that hopefully it makes a right triangle with the radius.
Okay, so you're going to basically use what?
Pythagorean theorem.
Okay, so I'm finding slant height, which is the hypotenuse of that. So let me set it up. And so I'm going to have, 8 squared plus 5 squared.
So 64 plus 25 is going to give us an 89.
And then so the slant height is the radical 89. I'm just going to leave it like that.
Sounds good.
Okay, there are units, so we'll round eventually. So surface area equals, let's substitute numbers in.
So pi times 5 squared, so 25.
I'm just going to substitute that in. So
Plus
pi
times 5 times radical 89. And again, guys, you could do the area of a base, which is pi r squared. And the half circumference, is the nice thing about that, it's really just the radius times pi instead of the whole diameter times pi. 5 pi times radical 89.
So this would be essentially the exact answer, and I'm going to explain why. I know these are both in terms of pi, but notice this has a radical. This does not. We know we can't combine if they don't have like radicals.
They don't have the exact same
okay?
radical, yeah.
So you can't say 30 pi radical 89. So we're just going to type that in the calculator. Actually, Miss Hochgraby is going to type it in for me.
All right, so the surface area approximately equals 226.73. And this is inches squared.
Good job.
All right. Now this next one says find the slant height. So let's take a look here. We're not finding the surface area. We're finding a new piece. Finding one of the parts of that formula. And we know it is a right cone. And we have the radius. And they give us the surface area here.
Okay,
so what's the first thing I probably still want to do?
Well, I see the fact that you're dealing with the right cone, and I see the word surface area. Let's write down the surface area formula. So surface area equals pi r squared plus pi rl. So here's what I'm thinking. I know the surface area. I know the radius, and the unknown is the slant height.
So really, I have everything I need to be able to
find
that.
So this is kind of working backwards. This is more of solving an algebraic equation, essentially.
Yeah.
All right, so let's substitute 336 pi for the surface area. Don't leave out the pi.
Right.
Okay, don't just put 336. Equals pi times the radius, which is 12, squared, plus pi times the radius, 12, times the slant height.
All right. Now, we know that we've got to simplify this a little bit probably before we do a whole lot with
moving stuff around. Let's do, so 336 pi. And I'm thinking, let's go ahead and square the 12 so I get 144 pi. And then I'm going to rewrite that as plus 12 pi L.
Love it. Now, can I combine these two?
No, but I know lots of people do. And
Yes,
the reason why is, again, kind of like the last slide. They are, yes, they have in terms of pi, but one has a variable, the other one does not. You can't combine. Those are not like terms.
Not like
so
terms.
I'm thinking, let's subtract 144 pi on both sides.
Okay. Now, these are like terms.
So when I subtract that, right, basically I'm taking 336 minus 144. Here's the deal, guys. Don't put 336 pi minus 144 pi. You don't need to do that.
Think about it like a variable. Think about it like an x. This
Uh-huh.
had been 336x minance 144x. I would subtract the coefficients, leave the variables.
So 192 pi, but don't leave out the pi. And again, there's no reason to type this stuff in your calculator, like the 336 pi, and get around an answer.
Right.
Now I want to get the L by itself, so I'm going to divide the whole side, or each side, by 12 pi. Now, here's what I'm seeing. I'm seeing that I'm dividing both sides by pi, and pi over pi is just going to cancel out.
Right.
So I'm essentially just doing 192 divided by 12, and I already had 192 in my calculator, so my slant height is 16.
Awesome.
Notice this is feet.
And this is feet. I was just going to say we have a label too. Notice that, we didn't really have to do much work with pi on this problem, as long as you know how to combine like terms and know how to, when you're dividing, know to cancel those pieces that are common in both the numerator.
And guys, this is something you could check. You could go back and put 16 back in for the slant height and see, does it end up getting your 336 pi?
Right. And we're not going to go ahead and check it right now, but just realizing that if I put the 16 here, this should, if I type that all in my calculator, it should give me my 336 pi. Perfect.
All right, we're going to switch gears a little bit. Okay, read the directions, and before you start writing down stuff and start figuring out, what are we dealing with this time?
All right, it says find the surface area of a regular triangular pyramid. Oh, so this one's not a cone.
No.
This is going back to what we did yesterday.
Okay, so surface area of a regular triangular pyramid. Now, when you see these words, okay, first of all, regular and pyramid, that's talking about the pyramid is regular. Not necessarily always the triangle. Okay. So we do have a pyramid that's regular, so we're going to write surface area formula.
Okay, so we have one base, the area of one base, plus half perimeter slant height.
And I'm going to take that back. This regular is going along with.
I
was thinking something else. I apologize, guys. I can correct my mistakes. So regular pyramid means that the base is also regular.
Right.
Okay. I had a
you were
brain
thinking,
fart.
because right doesn't mean that it's a right triangle. Regular does mean that it is.
Had a brain fart. Sorry.
That's okay.
All right. So here's the deal. We know it's going to be a triangle base, right? So what I often do is I draw that base. Okay. Especially anytime it's a polyhedron. So in other words, a prism or pyramid, draw that base so you can kind of see what you're dealing with. It's a regular triangle, so that basically tells us that all the sides are equal, all the angles are congruent as well.
Right.
Okay, let's read on. It says the base has side lengths of 12 centimeters.
So all the sides are 12.
Now, in the formula, the base area, you can find it with that.
Right.
The perimeter of the base, you can find it with that. Now the slant height, let's read on. It says, and the lateral edges are 9 centimeters. Okay, we haven't seen one like this. So we're gonna talk about that in just a minute. Let's find things that we already know.
Okay, so let's start with the base.
Okay.
Perimeter of the base will be pretty easy to find.
Yeah, I always like to start with the easiest pieces. I don't know about you. So that's gonna be
36.
All right, knock that out of the way. Now, we have an equilateral triangle, right?
So we could do 1/4 side squared radical 3.
And I know that's been used a little bit more recently, and some of you keep forgetting to use this, which is no big deal, but so much easier if you can do that. Okay, so the base area, so you get 12 squared, and you take a fourth of that.
Will be 36 radical 3.
All right, so I've got 2 of the 3 things I need. Now, let's talk about what they mean by lateral edges.
Okay.
Where are those located?
Well, here's the thing. When we talk about a lateral edge, really, of a cone, we're talking about connecting the vertex to a point that's on that circumference.
Okay.
But that's not really, I mean, a cone is a little bit different than a pyramid, because in a pyramid we have a polygon base. What we want to be careful with is that it is not talking about slant height.
No.
It says lateral edge for a reason.
And edges, remember, are your segments that connect a vertex to another vertex.
Right. So this is actually going from the vertex of the pyramid, from that top point of the pyramid, down to meet one of the vertices of that base.
Okay. So here's what I want you to think about. All right. I'm going to kind of feed off what Ms. Hokerby says. If you see lateral edges, these are essentially the edges or the sides of your lateral faces. Now, if you think about it in a pyramid, okay, if you kind of, and this is not exactly going to be the best visual, so bear with me. If I draw it, this is going to be a triangular pyramid. If I draw this in, okay, if I draw this just to kind of show you the visual, this is kind of your base, these are your lateral faces. And the lateral faces are always triangles, right?
Right.
If you connect from the vertex to the vertex on the base, this would be considered a lateral edge.
So that right there is what's 9.
That's what we're trying to find.
But that right there is not what we are trying to use in the formula, because in the formula we need the slant height. So the slant height, again, is the height of the face. So,
of the lateral face,
of
right?
the lateral face, yeah.
So what is the lateral face again? It's a triangle, right? Is it a special type of triangle?
And if it's a right pyramid, then it would be a isosceles triangle every time.
Or a regular pyramid. We're getting those two mixed up. Yeah. So if it's a regular pyramid, your lateral faces are always isosceles triangle. Kind of going back to this. So what are the congruent legs in a lateral face? It's the lateral edges. Okay. So these are both 9. Now, what would this be considered?
That's a base edge.
Which, do we know the base edge?
It's 12.
Yeah.
That's what they told us.
Okay, so again, these are your lateral edges. This is your base edge. All lateral faces are made up of the lateral edges, which are the congruent sides, and then the base edge. Okay? Right. It's kind of like if I connect this, and then this would be the base edge.
Right.
Now, what are we trying to find again? I'm all over the place.
We're trying to find the slant height.
Okay.
And to find the slant height, that's the height of that lateral face.
So I'm going to draw that in. And because this is isosceles, we've talked about this recently. What is the height of a isosceles triangle due to the base?
It divides it in half.
So these are going to be, that's going to be 6. So what are we going to use to find that?
We're going to use the Pythagorean theorem.
Now this time, the slant height is not the hypotenuse. That's a lot of times what it is.
Right.
So we're going to know the hypotenuse is 9. And then the rest of this stuff, we're going to set it up.
Right.
Okay, so I have, 81, and then over here 36. When I subtract that,
I get a 45 equals our L squared.
So L is
radical
45. And we're going to just leave it like that. There's really no need, since there's units, to make sure it's an exact form, which we could simplify that. All right, so we're going to put that in. Let's finish this up. We have the base area is?
Our 36 radical 3.
Plus
half of our perimeter, which was 36, times our radical 45.
And again, guys, you could simplify the radical 45 if you want to. You don't have to, though. So this is, I'm just going to simplify a little bit, though, and get 18 radical 45. And then when you type this in your calculator, just be very careful. Remember, when you put the radical sign, there's open parentheses, close it.
Right.
And then we get approximately,
let's see, 18 radical 45. Okay. You should get approximately 183.10. And this is centimeters squared.
So this one is a little bit more involved because they didn't give you the slant height and they didn't give you the height. Okay? When they give you the lateral edge, you really got to think, what does that mean? And drawing a visual. Guys, I know I've been stressing my students, draw the base, draw different things so you can see it better. Okay?
All right, last example. We are going to take a look at another pyramid. This one, it says we have a regular pentagonal pyramid. So what's the base?
Pentagon.
A pentagon, a regular pentagon.
And it's regular.
It has a base with sides of 8 inches.
Okay.
And they tell us the surface area. We're going to find the slant height of this pyramid. Now, since we know we're dealing with a regular pentagonal pyramid, I probably want to be thinking about what's the formula to find the surface area, because that's
that you're dealing with surface area in a pyramid. So surface area equals the area of the base plus 1/2 the perimeter of the base times the slant height. So here's what I do know. I know the surface area. I don't know the base area, but I could find it.
Okay.
I don't know the perimeter, but I could find that as well. And the slant height is that's really my go-to. That's what I'm trying to find.
Right.
So I better be able to find the base area and the perimeter.
Right.
Okay?
Okay, so let's talk about those pieces.
I'm going to start with the perimeter. Can I do that?
I love it.
So it's a pentagon base. So that means you're taking 5 sides times the side length of 8. So that's going to be 40.
Awesome. So we now have the perimeter. And what about the area of the base?
So I'm going to use the 1/2 the apothem times perimeter idea.
Okay. Now, should we draw the whole pentagon, or do you want to draw just the little right triangle part of the pentagon?
You can. I prefer just, because I don't want to draw the whole thing. I'm going to draw the right triangle that's formed by the apothem, the half the side length, basically.
Yeah. Oh, I wrote 1 over S. Half of the side, yeah.
And the radius, basically.
Love it. Now, what pieces do we know of that little right triangle?
Well, the side is 8, so half of that side is 4.
So I'm going to go ahead and just say this right here is 4.
And I need the apothem. I don't need to worry about the radius.
Don't need the radius. Now, in order to find these things, we know we're going to probably need to figure out what an angle measure is.
The central angle.
We can find the central angle of a pentagon pretty easily by taking what?
360 divided by 5, which gets you 72. And then cut that in half, and I get 36.
All right. So the central angle here is 36 degrees.
And guys, by this point, we've seen regular pentagons on. You may know that already.
And that's good.
All right, let's use trig, since it's not a special right triangle. So I'm going to use the tangent of 36 equals 4 over a.
Okay, and when we do a little cross multiplying, you end up with the apothem is going to equal 4 divided by tangent of 36.
Which is approximately 5.5055.
And we're going to leave that big long decimal in our calculator. Okay. Now, did that help me find the whole base area yet?
No. So I'm going to go to find, I'm going to find the base area, and I'm going to say 1/2 5.5. I'm just going to leave it like that.
Yeah.
5.0.
Goodness.
And then times the perimeter, which is 40. So basically, I'm taking that times 20, essentially, because a half of 40 is 20. So I'm going to take times 20, and that's about 110.1106.
Okay. And again, leave the big long decimal in your calculator. That's your base area. So right now, we know the surface area was 430. We know the base area was our 110.1106, etc. We know the perimeter was 40.
Hold on. Plus 1/2 perimeter.
Yep. What am I doing? Yes. I'm just crazy now. Okay. All right. So there's our base area plus 1/2. Our perimeter was 40. Thank you, Ms. Palermo.
That's all right.
And the slant height is what I'm trying to find.
Okay.
Okay. So what am I going to do next?
Well, I would go ahead and just do a half of the 40 and just call that 20.
I'm just going to even write it like this for right now.
Okay. And then what I'm thinking is I'm just solving for L. So I'm going to subtract that 110, the base area, from the surface area. So I'm going to put in my calculator 430 minus, and I'm going to do the answer recall button because I have it already in my calculator. And it's saying about 319.8894. And that's going to equal your 20L.
Okay.
And then I'm going to go ahead and divide by 20.
Loved.
So my surface area, slant height is approximately 15.99 inches. It's not square inches because you're talking about a linear unit.
Exactly.